Today we'll be talking about quantum computing, its foundations, and how Microsoft's Quantum Development Kit can help us apply those foundational concepts in reality. So why is everybody talking about quantum computing so much? Because it solves two problems that have been there throughout our journey as a humanity. Whatever we do, all things that we do are somehow related to optimizing something. Maybe the limited resources that we have, or the problems that we have to solve from science to finance, everything requires optimization. And the second plus point of quantum computing is quantum speed up. It not only solves those problems that we were never able to solve, but also solves them faster. So there are a few use cases where it is applied, like cryptography. It can improve the privacy of a user very much because of how protected it can keep the data. It can help in medicine and materials by discovering and creating new molecules that can be really helpful. Like if you look at the situation of the pandemic, it has been there for 2 years. What if we were able to get a vaccination in just the first few months of the pandemic? That would have been really good for us. And that is something what quantum computing can do. And if we And if we look at machine learning, it is also generally a problem of optimization. Whatever we solve using it is related to optimization. Um, and so whatever problems that we solve are related to optimization, and cryptography, medicine and materials, machine learning, searching big data, all of them are related to optimizing in one way or the other. So if we look at the problems that we face, like creating new chemicals, creating new catalysts that can help some processes, like making, we're using fossil fuels for so many years and they're almost about to get depleted. We need new sources of energy that are also environment friendly and sustainable. All of this can be solved with quantum computing because it makes things faster and solves those things that require a lot of computational power. So we'll be talking about what are the limitations of classical computing and how we can move towards quantum. We know that our computers work with two states, with 0 and 1. Either it's on or off. The electricity is flowing or it is not flowing. And with just these two things and different combinations of zeros and ones, we can do almost anything on our computers. Like we have predefined binary codes for the characters and numbers that we use. If we type anything on the screen, it's just a binary code behind. It's like a disco of electricity inside the computer where a sort of a flow of electrons is happening, and whatever we want is happening on the screen, and anything that we want to do is happening. Like from the emojis that we send to our friends on WhatsApp, or the code that we write on our computers that we execute on our computers and has solved so many problems, all of that is simply understood by the computer as zeros and ones. Like even if you click on your computer, that is also understood by 0 and 1. So everything that we do right now is primarily based on flow of the electricity in a computer, which is if it is flowing, it's 1, if not, it's 0. So all of this flow of the electricity is determined by a transistor. It is basically a semiconducting material which lets us allow the flow of electricity when we want to and not when we do not. Like we have conductors and insulators. Conductors only let electricity flow and insulators do not. With semiconductors, we can choose when we want the electrons to flow and when we don't. And because of these transistors and semiconductors, we are able to make computers that we have right now. All the classical computing that we see today is based on this basic concept. And through the last 50 years, the number of uh, transistors in a computer has been doubling with every 2 years. And if in 1970 there was in a coin just 1,000 transistors, then in the same area now there are around 16 billion transistors. That means that the size of the transistor is reducing very, very fast, almost exponentially. And now the stage is such that if we compare the atom and the transistors, then they're very, very close in size, like they're relative in terms of their size. And we can imagine it in form of an analogy where the human size can be considered that of an atom and the size of a building can be considered as that of the transistor. And they are relative. You can compare their sizes. So that's really small. And as it's getting smaller and smaller, we face physical constraints. That is, we cannot go any smaller. It is already very small. And at the smaller level, one more very exciting phenomenon takes place. At larger scale of you and me, we are governed by classical physics. But at smaller physics size, at the size of electrons and atoms, quantum physics is something that governs the laws of what will happen. So primarily what our transistor does is it creates a barrier when we do not want the electricity to flow through it, and it removes the barrier when we want it to flow. But as the size of the transistor is getting smaller, now the electrons can just pass through this barrier as if a human walks through a wall. It's like that on the smaller level. And with this, the concept on which classical computing is based breaks down, because now, even if there is a barrier, the electron could or could not flow to the other side. And this is a problem that we might face in future when the size of the transistor is very small, where we further cannot use classical computers. We will be able to use the ones we have right now, but we will not be able to advance. So that is why we need quantum computing to solve this physical limitation of classical computers and side by side do quantum speed up as well. I've told you the physical constraint part, but quantum speed up is something we'll be able to understand once we know on what basis the quantum computers work, and that is something we'll do later. Is there any question up until now? Um, If not, then we have a very special person with us over here today. She's a guest of honor. She's Devika Mehra, a software engineer at Microsoft, and she also loves the field of quantum computing. Today, she's here with us to answer a few questions that we might have, that many of you have filled in the forms that I shared. So, hi Devika, are you there?
Yeah, hello everyone. Thanks for joining in and hope everyone is doing fine and safe.
Yeah, I hope the same. So I'm really happy that you joined us. And I have collected a few questions in the form where the students registered, and they were really interested in knowing a lot of stuff from you. So, firstly, as we are students of a university, we all want to get placed in good companies. And we want sort of a roadmap about how to get into really good companies, which give us so many opportunities, like Microsoft. So, a lot of students had a question about how to get into Microsoft and what all they should look for, what all opportunities they should look at, and what should they study primarily. If somebody is not interested in DSA and has some other skills, can they still come into these big companies that help solve problems in the future? So if you could tell us something about this, it'll be great.
Sure. So, how to get into Microsoft? Of course, there are different opportunities. Maybe Microsoft comes to your own company, own organization, probably a university or your college. Then, of course, on campus is one of the greatest opportunities. That's how I got into Microsoft myself. I am a university hire, so I can totally relate to what is going on in your minds right now. Then of course that is not a constraint. So it's not like if you're not getting hired from university, there aren't much avenues. So there are career sites. You can go through, browse through the career site. There are internship opportunities. You can apply for those, probably get referrals from people you know in Microsoft. And that's how you can get into there. Now, what are the different kind of opportunities? Well, like any product-based company, there are different divisions. There are different products we handle. And of course, some of the products will be very close to how Microsoft works, like primarily internal tools, probably something related to corporation itself, and something which are outside facing. As well as this, there is services. So if you're interested in working directly with the customers, that's where you should land yourself. So a consultant is probably doing the job of a software engineer, probably working around the products which are already built in Microsoft and taking it to different geographical regions and selling it to customers, understanding what they need and customizing them accordingly. So you would be exploring a new division if you want that way. Now, what to study? So basically, that's a very good question. A lot of people are interested in knowing whether DSA is the only way. Well, I won't lie to you and say that DSA is not important. It definitely is. But is it a holy grail? No. Having said that, it doesn't mean that if you don't know DSA or you know DSA, it's for sure you're getting into Microsoft or any other tech company for that matter. Basically, DSA is a simple cut through, and sometimes some rounds are there in interview, which basically requires you just to code. So in those rounds, yes, data structure and algorithms might be handy, but building upon a story. So getting into any tech company, I would advise us to build upon a story that shows your dedication, your strengths, and try to emphasize on your weakness as well, which and probably just the idea of how you're improving them. So, learning about cutting edge technology, maybe doing development in your college years, building projects which speaks a volume about how team spirit is embedded in you, or how technologically advanced, or how cooperative you are. So, those kind of storylines you should build. And of course, a very attractive thing which you can put forward in front of your interview is your resume. So, try spending time over there and make, I would suggest a one pager resume so that that reflects everything about you and says much more than what you can actually speak. So even before you enter for your interview, resume is what is speaking for you. So make sure that is built up right. Yeah.
Well, this is really insightful. Like the story point was really apt because everyone's doing DSA. And if we have our own story, then we have something else to bring on the table as well.
Right.
Talking about bringing on table, people also want to know once they are in Microsoft, how is the culture over there? Like if they are in a particular department, and if they want to learn something new, go in another department, learn something else. And how is it different from other tech companies? Like what is like the culture over there that really binds you in? Like how is a day of work for you?
Sure. So how is basically my company allowing me to grow? So basically at Microsoft, what I feel is that you build your own career path. So you're carving it every day, and that's you are the owner of your career, and that is truly respected here. I myself in my 4 years of career has switched 3 roles, and that is only because the culture is receptive of the same. So you are ready, you are like basically allowed to make mistakes as in maybe you want to do one thing, but suddenly you feel, no, this is not what I want. And probably you try switching to another. Having said that, it's not that you keep on doing it every 2 months. Of course, that's not acceptable anywhere. You need to give yourself some time to learn and see whether things are working out for you. But if it doesn't, there is no stopper. It's not a deadline that if you have moved in certain path, you can't take a U-turn and go back and probably start with something else. So the culture is really open. Uh, Microsoft does pamper us a lot. They love us, I would say, and they really respect your career growth or the aspirations you have, especially for university hires. So they have hired us not to tell us what to do, rather the other way around, so that we innovate. And that innovation is something which is the catalyst here. So that actually helps us to grow even more. And the freedom Microsoft provides you to do the kind of work you want, plus how you want to do. So you're just given the kind of work you would have to achieve. So the end goal is fixed, but how do you achieve it? When do you achieve it? Within, of course, a speculated amount of deadlines is up to you. So nobody tells you or hands holds you to do or how to do things. So that's a good thing. Regarding how a particular day I would look like, so I'm basically in the security domain in Microsoft. So I personally try to see every morning what my mails are, how will my day be organized. Probably look through my ADO, that is our DevOps portal, what all tasks are assigned to me. See what is my next few hours will be occupied with. Try contacting to people, maybe to my juniors or seniors, trying to learn as much as I can. And of course, the learning culture is embedded in all of the employees and it's a must. So if you stop learning, probably you would want to leave that company or the company would want you to be gone out. So learning culture is very important, and that's what we primarily do the entire day. Of course, quantum is something which I pursued out of my interest. So that speaks volumes about how extra things are valued in Microsoft. So nobody stops me from learning such things. And certain part of my day does goes into things like that, which I want to work beyond my day. So that's how my entire day looks like.
That's really nice. Like all of the things you said, they're all related to individual growth in a way and innovation as well. So that is something that is something people look for, except for money, that they want in their life that gives them happiness and joy. So,
Mhm.
you were talking about quantum computing. What all resources and how is Microsoft as a platform where you can learn quantum computing? Like you said, you work in the security department, and I've seen that you've done a research in quantum key distribution, which is again related to security. So, like,
Yeah.
what piqued you, and how did you go about your research, and how can others also go through research if they want to, if they're interested in a particular topic? And right now with internet we have all the resources at our end, so what can we do as students at this age who want to pursue research in this field?
Sure. So, like most of the colleges in India, I feel, I'm not sure about how other regions work, but in India, we have something called projects at the end of our degree submission. So that's where I started with quantum. So one of my teachers suggested this as a topic. She wanted to suggest something a little different, but security was something I was always interested in. And that's how I owned my career in Microsoft, to be around security. So security was what I was searching for, where I can do some research, and that's how I landed myself in quantum. Why quantum computing will be devastating for the current security system, and that interested me. So I started learning more about it. Probably 6 months I just spent gathering all the research papers which are currently here, probably the internet sources, and sometimes I would want to clarify the some sources are really misleading. So be very intelligent when you are selecting those sources, so that you just don't get confused instead of gaining some knowledge. Then if you look at my paper, it's more of an exploratory product than of a new research being made, because that's probably one of my first papers I've written, and I am also learning. So try building upon that, and then you can do more research work. Try reading the recent papers first, I would say. Probably if you are researching today in 2021, probably from last 5 years, and only then go back if you don't see what you really need, because things get outdated very quickly in our industry. Everybody is in this field, so try keeping yourself updated. Then probably try seeing what is already existing, and if you can bring together things. So informational papers have their value as well. So don't think you have to come up with something really new to write a research paper. Probably your understanding is much more important to others than you think it is for you. So just gather those ideas and put them under one window, and that's how you can bring about a good research paper. uh, Regarding the other research component where you're really finding something, company like Microsoft will definitely help you, but of course you have to be the one who does everything. So you have to keep learning, keep exploring, try to contact the right people in the organization. Of course, it's much more difficult for a person who is outside Microsoft to do the same, and given the advantage you have, you can definitely take control of the learnings you can bring to yourself. Then regarding how basically what interests me in quantum, definitely it started with security, but I really feel the speed up it provides, the optimization it provides, which we can still do today without the quantum computer. That is what interests me the most. And for you guys, I would say really focus on all the subjects. So quantum computing is amalgamation of three. It's physics, mathematics, and computer. I personally feel a jack of all of these three, some basic knowledge like linear algebra, knowing about physics fundamentals and computer fundamentals will should be or could be something you can start with. Of course, you would have to build upon it. And there are plenty of resources available. There are videos from different universities. There are books available, so keep exploring, but just be a little cautious that you really go for a trusted source, because not everybody understands everything. And probably even if you know something, try watching those videos or taking those sessions, because everybody has something different to teach, their interpretation. So just be open to new ideas, I would say.
Yeah, like you said, even if we research on a topic that's already theoretically there, but we're providing with a new voice towards it, a different perspective that could help in maybe something else we don't know of as of now. So,
Yeah.
like, what do you think what the quantum computing looks like in the next few years? Like, there is so much it can do, like you said, optimization and speed up, and that's something we need in everything we do. So, like, what direction will it take, and how we as students could be an integral part of it?
Sure. So, first of all, I would say don't restrict yourself. Like, don't think that first day itself you will get to build a quantum computer and probably you do be doing something revolutionary. Start small, I would say, and that brings up a lot of change. So, there are open source contributions you can do. Probably these things don't require you to know quantum computing also. You might be just a good coder and you will be able to contribute, like for our QDK, that is quantum development kit. There are open source resources, so you can contribute to that as well and keep learning. Regarding how it will shape in future, I think the optimizations are something which are already happening. It's just that some things we are aware of, some things we are not. So the optimization is basically something which I am very confident that in next 5 years to 10 years, that will revolutionize the way we code. And regarding fully fledged quantum computers, of course, that would take a little while, but they will be there. So we are seeing organizations actually building up, like Google, we mentioned in the beginning, and there'll be other fields which will be bringing up the same. Also, the kind of qubits. So there are different type of qubits. You can learn more about them. So the way they change or the way they can be manipulated is something, if that interests you, then that can be another field to explore.
Yeah, like that's really insightful for us to look at different directions. That'll be all from my side. If anybody else has any questions as of now, you can please unmute and ask. And if not, then we can continue. You can ask in a minute or so.
Yeah, I had a. Am I audible?
Yeah, you are. Please go ahead.
Yeah. Hi, hello everyone. Good evening. I had a question for Devika ma'am. What is the timeline that we're expecting quantum computing to reach the desktop and handheld devices?
Oh, well, we don't have a timeline of that sort, but yes, we are uh, pacing up really fast. So, probably 3 to 4 years back, we couldn't even imagine what we are achieving today. So, definitely in next 10 years, and that's my speculation, is that it has nothing to do with
Um, I'm audible, right?
Yeah.
Well, I think she's stuck, so I can continue with the answer. As of now, we have quantum hardware in place. It is not really going to replace classical computing as of now. It will complement it in solving those problems that it cannot as of now. And maybe in the future, we don't know. It can be possible that we never knew we'll be having phones in our hands all day in the past years if we look back. So even in the future, we could have quantum computer based phones or stuff like that in our hands. But as of now, we do have quantum hardware, which we can access through cloud computing sources like Azure. That is something we'll talk through the presentation. So we are in a direction where we can use quantum hardware to solve certain problems, but not all. So we're progressing, we're in the right direction, and we're perhaps in a point where we have so many directions to follow. And it's a future that really depends on us, the people who are in the workforce right now, to give it a direction where things we never thought could be done will be done. So the discussion was till here only. If anybody else has any questions, they can put up in the chat and we can have a discussion later on. Uh, Continuing, I've explained what classical computing was, what were its limitations, and how quantum computing could be an answer to it. So, we do need to understand the basics of quantum computing on which it depends. So, okay, so we were talking about the transistor getting smaller to the size of the atom, where quantum physics works now, not the normal physics that we know. So, if there is a particle like an electron and it goes through this setup of double slit experiment, um, so what do you expect will happen? When it passes through the two slits, will everything go like in option A, just behind the screen, just behind the holes that there are, the two holes, or like B, we get a wave like pattern with light in certain places and darkness in certain places, like we've seen with waves, if we remember the physics we studied in school. So, if anybody has any guess, A or B, what do you think? You could let me know in the chat or just say. So, like I said, um, at the smaller levels, everything works differently. If in A we would have expected to throw a marble, then the marble would just go behind through the hole and on the screen, and we'll get something like A. But for an electron, we get something like option B, which proposes that electron is not a normal particle. It has wave-like character associated with it, where the it's like a wave, and where two waves meet in a way that they add up to each other, we get the white spot, and in places where they cancel each other out, we get the dark spot. So electrons exhibit both particle and wave nature. Because of this thing, we can leverage quantum computing and do stuff with it. This is the basic concept on which it depends. So this is what happens. Like if we uh, throw one electron, we'll get random pattern initially, and when we've thrown a lot of them through this double slit experiment, we'll get something like a wave, which we get for light as well. So electrons are both particles and waves, like so. This is the pattern we get. This is a wave, and this is how we got in the slit experiment. And because of this property, it's both a particle and a wave, we are able to solve things, like I've been saying for a while now, like we've not done before. So now imagine classical bit as 0 and 1, like a switch. You can switch it and switch it off. And qubit is basically the quantum analogous of the classical bit. In quantum computing, the smallest bit that we use for information is a qubit. And you can imagine it as a dial. It's 1, it's 0, and it's everything in between: a normal number, a complex number, imaginary number, just anything. And a qubit is like in all of these states at the same time. But when we measure it, it falls back to 1 or 0, and that's again like the classical bit. So, like quantum physics is a general physics whose one small case is the normal classical physics we know. Similarly, qubit also collapses into a classical bit, but because it can be in multiple states at a time, it gives us the opportunity of looking at all these states at the same time, and being able to look at more states in a problem, and that is why it gets solved faster. Now you'll see on the screen there is some weird design, like it's called ket, a ket 0 plus b ket 1. It's a linear combination sort of an equation which is nothing but probabilistic in nature. Like the probability of the qubit being 0 is a, and of being 1 is b, and it can be any. It's in a state where it's anything, 0 1, anything in between, but when we measure it's 0 or 1. um, a better way of understanding what I just said now is imagining a coin and toss it. Right now, it's everything. It's heads and it's tails. It's in superposition of both heads and tails. But when we stop it and when we measure it, it's either tails or heads. And this superposition is one fundamental concept because on which quantum computing depends. And this allows us to look at a lot of states at with lesser bits. So classical bits and quantum bits, if we compare them, classical bits are deterministic, 0 or 1, and quantum bits are probabilistic. They can be anything until we measure them, and then they become again 0 and 1. So this is a little mathematics, but it's very simple to understand how it's just not something really difficult, quantum computing. In small terms, it's just basic probability. If you look at 0 ket, it is basically that the wave function, we just determined that electron is also wave. So we determine it as a wave function, a ket 0 plus b ket 1. And ket 0 basically means that the probability of the wave being 0 is 1. So the qubit is 0. It is not 0, 1, and everything in between, it's 0. And 1 ket means that the probability of the qubit being 1 is 100%. And if you see the wave function over here, uh, ultimately we get a lot of the ket that we see 1 and 1 0 in column for 0 ket means it's 0, and 0 1 is for 1. And if instead of 0 and 1 we have any other random number, it is the probability for of being in that particular state. So if you see over here, a is the probability of the qubit being in 0, and b is that of 1. And we have to square it because a and b are complex numbers, and if we add, the total probability does not equal to 1. But when we square them and then add, then it's equal to 1. And it's just simply probabilistic. And because of probabilistic, we are again able to look at more permutations and combinations and solve problems. So till now we've discussed two of these phenomenons on the screen: interference and superposition. And these three concepts together make quantum computing possible because of how they, in small ways, tweak what we know of classical computing. So, um, if we look at superposition, there's a thought experiment which is really cool. Like the tossing of the coin, we imagined it's both heads and tails, and when we measure it, it's head or tail. Similarly, there's Schrodinger's cat. The thought experiment goes like this: that in a box, we keep a cat, and there is some poisonous thing over there, and the cat might eat it, it might not eat it. It's in the box, we don't know what happens. So while we don't know, we can assume that the cat is both alive and dead at the same time. It's only when we open the box that we're able to see what it is. And it's like the state of superposition collapses into one state. We like when the box is closed, we are probabilistic in nature. The cat can be alive, can be dead, so it's both. But when we open it, it becomes deterministic. And that's how quantum computing is a more general version of classical computing. And superposition is something on which it heavily depends. So, quantum speed up is something we've been talking for a while now. I'll give you an analogy for it, which will help you understand what it means. So, we have a classical bit, and in classical computers, suppose you're doing a linear search. So imagine this in the first picture, that one boy is looking for something. He goes into a room and he looks at different places, in the cupboard, under the bed, in drawers, and he looks in the drawers in the end, and whatever he's looking for was in the drawer. So it took him a lot of time to find the thing it was looking for. It was moving linearly, checking all the possibilities one by one. But in quantum computing, we have a qubit. The qubit can be at many states at the same time. In the other picture, imagine there are three places where the thing can be, and there are three people to look for it. And they go there at the same time. The ones who did not find the thing say we did not, and the one who found said we found. And in just one time complexity unit, if we take it, comparing to the first one, then in just one unit of that time, they're able to find the thing. So that's how there was a quantum speed up. That person, the first person, had to look for three different places. And in the second one, we were able to just go there and find it in the first instance. So it quantum speed up is like because of the qubit being in superposition, it was in all the states, and in the one state that it was found, it collapses to that state. And the other concept being interference, where waves that match each other add up and which do not, they cancelize. So what interference does is it amplifies those states which have more probability of solving the problem, and those states which cannot solve the problem get cancelled. And that is how we are remained with lesser states in the end. And therefore quantum speed up can happen because of these two major concepts. So here, like in classical bit, if we have just two bits, they can be 0 or 1. But in qubits, they can be in so many states at the same time, 0, 0, 0, 1, 1, 0, 1, 1, basically to n. So if we have just 3 quantum bits, they are equal to 8 classical bits, right? Because for the classical one, we have to have all these 4 options with us. But in quantum, we just need 1 qubit, and it's in all of these states at the same time until and unless we measure it. So just 3 quantum bits is equal to 8. This doesn't look that big, but as you can see, as we increase the number of quantum bits, the states of classical bits are exponentially increasing. So obviously, the quantum computers can solve things faster than classical bits because they can look at more states with lesser number of qubits, right? So if we look at one optimization problem we're taught in universities is traveling salesman problem. finding the shortest distance between different routes, and then taking that one. It's a permutation and combination problem. With lesser number, it's okay, but as the number of places to visit increases, to find the shortest distance becomes really tough because we cannot look at all the states of permutation and combination. But with quantum bits, we can look at a lot of states. If you look at 300 quantum bits, they are equal to something to the power 90 of classical bits. So, though we're not at a stage where we use 300 qubits, we're around somewhere around 30 to 50 with different companies claim to have made quantum hardware with this much of qubits. But if you look, this direction is promises something that we can solve using it. So, till now we've talked about interference and superposition. Entanglement is also a concept that we'll talk later. And these are the three concepts on which quantum computing depends. Now, we've been talking about Microsoft QDK. So, that's nothing but a quantum development kit where there is a simple coding language wherein we can code the things we want, these phenomenons, in fact, and then look at the result. So I'll guide you step by step how you can do it. If you want to do it right now, you can. If you want to do later, that is also okay. QDK basically consists of two things. Q Sharp, it's the programming language of quantum computing developed by Microsoft. There are others as well of different companies, but today we'll be talking about Microsoft's language. And Azure Quantum, the cloud platform with whose help we can run our codes on real quantum hardware. Quantum hardware does exist, but it does not exist in form of a computer till now. We never know about the future. And we use these things to solve optimization problems that we've been discussing so far, and other computing problems like finding new chemical molecules for something. So for being able to code, you need a .NET Core 3.1 version installed. It will help us build the app that we're trying to. And you need Visual Studio Code because that is where we can install Q Sharp as an extension. So I've done this already. Q Sharp is a domain specific language. Like we have HTML and it's used for making websites only, majorly. And Q Sharp is similarly used for solving quantum algorithms and other stuff. So QDK also provides us with a lot of libraries because like Devika had also said, QDK is somewhere that which is open source and you can contribute in it. So we have a lot of libraries already made which solve problems. We have libraries like quantum chemistry, which has functions we can call and solve some problems. Then we have targets. We have Azure Quantum, on which we can run our algorithms on different sort of quantum computers. I mean quantum hardware. Like there are different providers like IonQ and Honeywell, where we can run our problems over there. And Q Sharp is a very flexible language. You can code it with Python and other programs that we already know. So right now, quantum computing is very much integratable with the classical setup we have. So what we have right now in itself is beyond imagination and is really cool. It's a good milestone to look at. But quantum computers is something which the future proposes us with. So whenever you want to create a program of Q Sharp in Visual Studio Code, these are the few steps that you'll have to follow. Just click on the view and then the command palette. There'll be an option. Click on create new project. There'll be another option. Click on standalone console application. And then you just need to name the project file where you're working and a new project will open. So I did this basic stuff. To make a quantum hello program, it's nothing. It just says hello world, like the first thing that we do whenever we learn coding in any language. So if you can see in the directory, quantum hello is created, and in it there are two files, program.qs and quantum hello.csproj. That one, the other one is for just setting some specifications. The real coding that we do is in program.qs. So I'll explain you how it works. It pretty much looks like C in syntax, and namespace does exactly what it does in C. Open helps us to import all the functions in a particular library. So over here we're calling functions from Microsoft Quantum Canon and Intrinsic, and we can use those functions directly in our code. Entry point is what our program runs when we call it. So whenever we'll run this program, whatever operation is under entry point will be run. So operation is a keyword, and it helps us define, you can imagine as something like a function. Here we name it as say hello, and there are brackets. There's nothing inside it, so there are no arguments. Then we have the word unit. Unit is analogous to void in C. It means that nothing will be returned from this function or operation. And then message is something we get from the intrinsic library we imported above, and it just helps us to print the word, the sentence hello quantum world on our screen. So like I told you that in installations you have to have .NET to build the app. So to once you've coded this, when you want to build the app, you just run the command .NET run on your terminal, and you can see you get hello quantum world printed on your screen. So this is the basic syntax which we follow over here, and we'll look into a deeper code. So till now we've been talking about superposition, being that the qubit is at multiple states, and when we measure it, it's at one particular stage. So in this code, we have called a lot of libraries that we're using, and nothing is happening of that greater level. We just make a function and it returns a result. Over here, it does not say unit, which means void. Over here, it says result, means something will be returned. Then in the 12th line, you can see use q equal to qubit. It does assign a qubit to the variable q. So now q is a qubit. It can be in any state between 0 and 1. Then the message is printed, qubit is allocated. We're using a function dump machine. I'll show you the result on the other slide. Dump machine is called from the diagnostics library. What it does is it just lets us know what all states the qubit is at the state we're at. So we just allocated q to a qubit. So dump machine will let us know what is the state of the qubit like. We've been talking about it'll be something between 0 and 1. What exactly will it be? Then HQ is a function that helps us to put that qubit into superposition. So whenever we assign q a variable to qubit, it will always be 0 by default, so that we have a starting point to work with. We know that whenever we assign a qubit to a variable, it will be 0, and that is our starting point. By using the function HQ, it will be put in superposition. So now the qubit is anything between 0 and 1. Then we measure it with the function MQ, and we'll get one result. The superposition will collapse into 0 or 1, and the random bit that we will get by using the function MQ will be 0 or 1. And then when we reset the qubit again, it will again be 0, because the default state of a qubit is 0. I hope it made sense to you. Even if it didn't, it's really good that we've understood till this level also. So this is what happens. So when the qubit is allocated, it is always given the state 1. So here you can see 0 ket, 1 plus 0 I. As I told you, the A the coefficient that was in front of 0 is a complex number. Here it's 1 plus 0i, which means 1. And for 1, it is 0 plus 0i, which means 0. So our qubit is in the state of 1. This is simple probability. These complex numbers are just telling the probability of being in state 0 and 1. So after we apply the superposition, we get this complex number, and when we take its square to get the probability, as you can see here, the chances of being in 0 and 1 are 50-50 because it's in superposition. And then when we measure this qubit, it will collapse into one of the states, 0 and 1. So either it will be 0 or it will be 1. And in this case, it came out to be 1. And when we reset the qubit, as I said, the default is 0. So the qubit will be 0. And that's why we get 1 over here as the probability. So this is one function, one program that we coded, which explains superposition. So the concept I was talking about is not just theoretic. You can apply it using a program. So we were talking about this last other function, other phenomenon called entanglement that helps with quantum computing. So entanglement is really cool. Like we imagined that we toss a coin and it's in any state and then collapses into one. Now imagine that you have two coins and you toss both of them and you measure one of them to be 0. And you can be sure without even measuring the other coin that it will be the opposite one because they are correlated. And this is a very spooky phenomenon in terms of Einstein, that we determined the state of one of the qubits, and without even measuring the other one, we already are sure what it will be because they were entangled. Even if these two coins are on different planets, the result will be same. And this helps us with communicating at such a high speed. We just checked the result over here, and we're sure of what the result will be very far off. That is why Einstein was a bit skeptic of it, because according to him, we can communicate at max at the speed of light. So a cool example of, again, understanding what this is. Suppose me and my brother are living far away as of now, and we are entangled because we are siblings. And if we go for shopping, if I buy the first t-shirt, then I can be sure of the fact that he'll buy the other one. Or maybe, and it's not like in entanglement that if it has to be the opposite. It's just that the two are correlated. They could be correlated in a way that they could be the same as well. And in cases of siblings, it's usually the same. They fight over the same thing. So this was just an analogy to explain how it works. If we look in a bit more technical term, then photons are entangled together, and then imagine that they're separated. And then, okay, Alice and Bob take one photon each. And if Alice measures the state of her photon, then she can be sure of the state of the photon that Bob has because they are correlated. It's not necessary that they'll be opposite, they can be same as well. It depends on how they were correlated. So this was all about the three basic functions that we have, three basic phenomena on which our quantum computing is based. So till now, does anyone has any sort of doubt? If you have, you can unmute and say, I'll wait for a minute or so. And even if you've come along through this much, it's good enough. What you know is all the basic phenomena on which quantum computing depends. And if you go out to explore it further, I'm sure you will be able to understand what it's talking about, because it's just basically these three things that it depends on. So if anyone has any doubt. Okay, so now these were the phenomenons. I'll tell you about simple things that we can do as something that solves the problem on a quantum computer. Till now, what the screenshots that I showed you were from my local computer only. So it works on my computer. You'll be thinking, okay, fine, you're coding in a quantum language, programming language, but where does the computer come into play? So these programs are something we can run on classical computers as of now because they're easy ones. Tough ones require quantum hardware, and that is very easy to connect with. We just have to connect with the Azure quantum platform, and from our terminal only we can run it on the cloud, and the cloud will run it on the quantum hardware, and we'll get our result on our terminal itself. So you can see quantum random number generator. It is a very simple algorithm that we can code, and it does nothing. As the name suggests, it just generates a random number. How it's cool is because it's truly random if it's generated on a quantum computer, because when we generate random numbers on our classical computers, they have um, they are pseudo random. They're not exactly random because the computer usually uses the CPU time at that particular time as a random thing, and with the help of it generates a random number. But using the quantum version of it, what we generate is truly random because there was no starting point to it from which we came to the random number. uh, I would like to show you the code for it, but it's not over here. It was on my laptop and I had to change. So I'll be sending some resources after the session. So I'll attach the code over here. The code that I explained till now is the basic. And if you've understood what I've just explained, you will be able to go through the code later on and understand what it's saying. And even if you have any doubt, you can just let me know. Um, so yeah, like I was saying, till now we were just working on our computer. Microsoft Azure helps us to get the result on our terminal itself, but it's solved on quantum hardware, which is provided by different companies who are working on making quantum hardware. There are many because a lot of research is going on in this field, and that too a lot of different things are going on. Some people work on quantum computing in the coding part, and some work on making the quantum hardwares. And over here on Microsoft Azure, we get best of the both worlds. We can develop codes on our computers and run them on quantum hardware made by other companies. So for that, we have to do a few simple steps. If you would like to do, you could. You just need to go on your Azure service, Azure portal, and over there you just need to create a resource. A new resource will be created. In that, you need to search for Azure Quantum. When you do, you will get this option. You just need to select it and create your Azure Quantum. It's just like a workspace. So whenever you will be calling a command on your computer, this workspace will be used on the cloud to get the providers. So on creating, it will ask you for some details like your subscription and other stuff that you can add. And beware, this is paid. The subscription is paid. A free account gets you a few dollars. You can try it out, but be sure that you do not exhaust your free resources and still work with this, because it can cost you something. And these are just a few commands. Once you've set up that workspace that I showed you, you can just run these simple commands on your computer, and you'll get the result of the same algorithms that we run on our computer from a quantum hardware. Uh, AZ login just takes your credentials, and the second one sets your subscription. Uh, then AZ Quantum Workspace just tells which workspace you were working on, so that your quantum account knows which resource to send your code to and get an output from. The last two are uh, running the code on a quantum simulator and on a real quantum hardware. You can first run your your code on a simulator, because that allows you to know if you're doing the correct thing or not. Uh, but the simulator will give you a deterministic sort of a result. Then when you're sure that your code is doing exactly what you want it to do, you can run it on a quantum hardware, where you'll get the result from a real quantum hardware. So I cannot show this to you right now, but if you follow the steps on these two slides, then you'll be good to go, because it's exactly the way I showed you how to code is followed over here as well. So this would be almost the end of our meeting, because I've told you the very basics of what quantum computing depends on. And uh, all that I've told you, because of that, you can explore certain things on your own as well. Like now you're capable enough of understanding Grover's algorithm or Shor's algorithm that already exist, and you will understand it because it all depends on these concepts only. So Grover's algorithm is a quantum algorithm that helps you sort a database, search something in an unsorted database in a faster way. And Shor's period finding algorithm is something that everyone is so scared of, because it has the capability of breaking our current security that uses RSA. RSA depends on prime factors, and the fact that finding those prime factors is very tough. But because quantum computers use qubits and can measure a lot of states at one single time, it makes them capable enough of exploring a lot of states, a lot of factors of that number, and come up to a number. It's still in its developing stage. Theoretically, it's there, but we need the hardware. But if it is there, RSA can be broken. And that is why we also have post quantum security protocols uh, that are there, that are also in research phase. So these are some things that you can look at. You might have also heard about quantum internet. It will be something that, again, internet is already revolutionary. It will make it faster and optimize it. And quantum internet further depends on just two basic concepts. Super dense coding and quantum teleportation. It sounds lengthy, but if you go through it, it'll be very much dependent on what we've just discussed. So from this meeting, you have the basic idea of what quantum computing works on. And if you are interested in it, these are a few things you can explore just now, after just these concepts, and you'll be good to understand. That'll be all from my side. Thank you for being here. Thank you for waiting, even with the slight inconvenience we had in the beginning. If anyone has any questions, you can ask me. Otherwise, we can end the meeting. And I'll be sending you emails with further resources that you can go through if you're interested in it. Thank you. So if there's any doubt, you can ask me. Um, I think there is no doubt. So we can end the call over here. And I've mailed you stuff in the past as well. So if you have anything, you can mail me back if there is any doubt. Thank you for spending your time here with me.